Hey there. So welcome to this third video of this unit. We're going to be talking finally about the other set of trig functions that we're going to need to know about. So there's going to be a lot of definitions in this video. That makes it an especially good one to take notes on. Also, we'll say a little bit about the Pythagorean identity, but we'll save most of that for class. Okay, so just to start with the Pythagorean trig identity, this is the most important formula when it comes to the trig functions and using them to solve equations in general. So we're not going to see much application of this at the moment, but right now I want you to think about why this is true. So you probably remember the Pythagorean theorem. It's the one with right triangles. It says that if I have a right triangle and I label the sides A and B that are not the hypotenuse, and I label the hypotenuse C, then I get that just, classic thing, a squared plus b squared equals c squared. Okay, so as we've talked about, many times before, in the unit circle definition of trig, we can put a right triangle in there, and that's helped us think about and prove things about these trig functions. But if I just use that Pythagorean theorem, then I come up with a pretty important identity. So in the right triangle in the unit circle, I can have any angle theta now, and that makes the hypotenuse equal to 1 because it's the unit circle, it has radius 1. And when that's the case, the bottom side of this triangle is cosine of theta, and the right side of this triangle is sine of theta, because those end up being the coordinates of this point on the outside of the circle, right? All familiar stuff. But if we use Pythagorean theorem on this triangle, we get the formula sine of theta squared plus cosine of theta squared equals 1 squared. Right? Because this is now our A, this is now our B, and this is now our C. And 1 squared, of course, is just 1. So changing this around a little bit, this is how you're going to see this in textbooks and in future classes. So the angle could be anything, as I said, any angle theta. But we're going to, instead of writing sine of theta squared in such an awkward way where I have to use parentheses, we're going to move that 2 over by the sign. So it means the same thing. It still means that I'm first taking sine of theta and then I'm squaring it. But it means that I don't have to use parentheses. And I absolutely don't want to put the square by the theta because then it looks like I'm taking sine of theta squared. Right, so it would be like first squaring and then taking sine. But that's not what I want to do, right? I want to first take sine and then square it. And that order is important. So this is just another way to write what I have handwritten over here. Okay, so that's all I want us to do with Pythag identity because we're going to be doing a lot more in class. Okay, so now for the definitions of these other functions. First, we're going to talk about the reciprocal trig functions. So we know about sine, cosine, and tangent, but if I take any of those functions and take the reciprocal of it, meaning literally 1 divided by that function, then I get 3 more functions, and these all have names, and we're going to need to be familiar with those names because they're going to pop up all over calculus class and other classes as well. So the names of these functions are secant or SEC, cosecant or CSC, and cotangent, COT. Okay, so like I said, they're all reciprocals of the previous ones, but in a kind of funny way, so make sure you write down these definitions. Secant of theta is 1 divided by cosine of theta. Cosecant of theta equals 1 divided by sine of theta, and cotangent of theta is 1 divided by tangent of theta. And if you think about it, tangent is already sine over cosine, so when I flip that fraction around, I get cosine divided by sine. So that's another way that I can think of or define cotangent, is cosine over sine. Okay, this is not what you would expect. It's not what any reasonable person would expect this definition to be, right? Because I'm associating secant as the reciprocal of cosine, and cosecant is the reciprocal of sine. Okay, that seems obviously backwards. It seems like I made a mistake, but I did not make a mistake. That is how secant and cosecant are defined. At least cotangent makes sense, right? It's the opposite, or it's the reciprocal of tangent. Why is it defined this way? Well, for kind of convoluted reasons having to do what the word secant actually means and going back 300 years. But it's not really worth going into that reason, and the reason really isn't going to help you remember that it's the way it is. You're just going to have to remember that it's a little bit backwards that way. And that's certainly how I remember it, as just being backwards in that way. So it's an unfortunate fact of history, but it's one that we have to deal with because it's in all the textbooks. Okay, so those functions aren't too bad, and you're gonna see at the end that, I mean, we know special values of sine, cosine, and tangent, so you take reciprocal of those, and now we know a bunch of special values for secant, cosecant, and cotangent. And as you can imagine, we're gonna get lots of practice with that in class, so you'll have to have your unit circles handy. Okay, the last thing we're gonna talk about are inverse trig functions. Okay, so we've already talked about inverse functions quite a bit before, right? It's how we defined logarithms, for example. A logarithm is an inverse of an exponential function. So now we're going to be taking inverses of the trig functions. So first off, what does an inverse function do again? Well, it switches inputs and outputs, right? So sine, cosine, and tangent, they all take angles as inputs, which we've been calling theta, and they output a coordinate, the x coordinate, the y coordinate, or if it's tangent, y divided by x, right? So a quotient of two coordinates. So the inverse trig functions are going to have to go the other way. Now, there's two problems that we're going to have to deal with because these functions off the bat are not actually invertible yet, right? They have both of the problems that you can have that would make something fail to be invertible. So we're going to have to deal with that in order to define these inverse functions. The first problem is not so bad, right? Sine and cosine, they don't spit out anything, right? They don't output any number. They can only output a number that's between -1 and 1, right? That's the range of sine and cosine. The range of both of those functions is -1 to 1. So going the other way around, that means that the inverse sine and inverse cosine, and yeah, that is what we're going to be calling these functions, they can only input numbers that are between -1 and 1, right? So I can't plug in 2 into inverse sine because sine never outputs the number 2. It's pretty simple as that. So that one's not too bad. The bigger problem is that for sine and cosine and tangent, you can have many inputs going to the same thing. Okay. Specifically, right, there are many angles that go to the same point on the unit circle, right? You can always add 2 pi and subtract 2 pi. But even different points on the unit circle can have the same x coordinate, or they can have the same y coordinate, right? So that's a big problem, because when we want to go the other way, we can't have an input going to multiple outputs, and that would be the case. We need a way of fixing this problem. The way that we fix this problem is actually pretty simple. We're just going to restrict the range of these functions. So we're saying you can't output anything. You can only output an angle that's in a specific range. And that range will depend on whether we're using inverse cosine or we're using inverse sine. Those are ranges that we'll have to remember. So here's an example. This is a little hard to follow. And by the way, I expect that there will be questions on this in class. So here's an example of this, right? Say I want to compute cosine inverse, or inverse cosine of 1/2. Okay, so what does that mean? I'm thinking in my head that going backwards, I'm looking for the theta where cosine of theta equals 1/2, right? So I first set the solution equal to theta, kind of a bit like I'm solving a log problem. I need to give that a name, And then I need to flip the function around, or flip the equation around, so that I'm solving cosine of theta equals 1/2. Okay, that means I get out my unit circle, or I draw a unit circle, and I look and see that on the unit circle, I'm looking at the x coordinate, because it's cosine, and there are 2 points on the unit circle that have that particular x value, up at the top and up at the bottom, and both of those points have infinitely many angles that go to them, right? Again, I can always add 2 pi or subtract 2 pi. So the top point is like, it could be pi over 3, it could be 7 pi over 3, it could be 13 pi over 3, and the list goes on endlessly. Same thing for this point down here. So that's a problem. I have more than one solution, and I can't have more than one output to the inverse cosine function. So what do? Well, by definition, we pick the solution that's between 0 and pi. Okay, so this is a convention. This is part of the definition of this function. We can't let it be anything. So we take only the unique solution that's between 0 and pi. Visually, that means we're sticking to the top half of the circle. So that means that I must be using the top point. And I'm only allowing, instead of picking all the possible angles, I pick the angle that's between 0 and pi. So that's pi over 3, right? That's how we would normally label that point, unless I was being weird and subtracting 2 pi and adding 2 pi, right? So there's kind of a sense to be made out of this. That means that inverse cosine of 1/2 is equal to pi over 3. All right, well, it's pretty similar for sine inverse. So here are the actual formal definitions, and this would be a great thing to write down. Cosine inverse of, let's say, A equals the unique solution theta to the equation cosine of theta equals A. So that's getting at the idea again, inverse functions flip things around. But I pick the solution that's between 0 and pi. And there's always going to be exactly 1, as long as I'm plugging in a number between -1 and 1, which I'm calling the domain of inverse cosine. Inverse sine, same thing, but I have to pick my range a little differently. So it's going to equal the unique solution to the equation sine of theta equals A, that's between minus pi over 2 and pi over 2. So the reason for that, actually, again, going back up to the circle, we're restricting ourselves to, instead of the top half of the circle, for inverse sine, we're going to restrict ourselves to the right half of the circle. And that has to do with getting the full range of possible values of sine and cosine, right? So for cosine, I want to capture all the possible x coordinates that I could get, -1 to 1, and have a unique angle for each of those. So that means that I would want to pick either the top half or the bottom half, and just by convention, I pick the top half. For sine, I again want to capture the full possible values, -1 to 1. So I would either have to use the left half or the right half, because sine is y coordinate now. So we just pick the right half, and we just decide that those angles are going to only be between minus pi over 2 and pi over 2. So these are conventions that are chosen for us, and they're also, of course, the conventions that our calculator are going to use. So when we plug these things into their calculator, we need to understand that that's the range of values that it's going to spit out for us. Okay, lastly, so tan inverse, same sort of deal. It's picking the unique solution to tangent of theta equals A, and like inverse sine, it's going to stay between minus pi over 2 and pi over 2. Again, because that's going to capture the full range of possible values of tangent. Remember that tangent actually has a range that's equal to minus infinity to infinity. So when we flip that around and make the inverse function, the domain of inverse tangent can actually be anything. It doesn't have the same domain restriction. And you actually get this very nice function where you can put in any x value, and you'll get out a number that's between minus pi over 2 and pi over 2. Okay, I thought I would actually show you the graphs of these functions. These functions aren't used very often in modeling, except for maybe the possibility of inverse tan. I would say that if there's a function, I mean this is a broad statement, but if there's a trig function besides sine and cosine that gets used most often, I think in the real world, I think it's actually inverse tangent, weirdly enough. It actually gets used all the time, especially in a lot of like real world like carpentry problems and problems about building stuff. So just to show you the graphs real quick, I put up the graph of cosine inverse and sine inverse. I didn't put up the graph of tan inverse, but I'll show that one to you in class. What I've done here actually, remember that, so the blue graph here on the left, that's actually the original graph of cosine, if you remember. So that's a familiar one for us. And when you're finding inverse functions, there is this process you do to the graph. I think I've talked about this with many of you, that it's flipping the graph over the y equals x diagonal. Okay, and in fact, that's actually what happened here. It's a little hard to see, but what's going on here is that we've taken the graph of cosine, chopped off everything outside of 0 to pi, so from here to a part of the graph we're not seeing, and then flipped that part over the diagonal y equals x. And if you do that, you'll get this red graph, and the red graph is the graph of cosine inverse. And similar thing going on for sine, just taking the part of sine between minus pi over 2 and pi over 2, and flipping that over the diagonal. So I wouldn't say that you need to memorize these graphs or anything. Again, these functions don't come up very often in modeling, but it's good to know that that same thing that's always true about inverse functions is true here as well. Okay, so not much going on, by the way, for homework. I just put a couple of problems that tests that we kind of get what these definitions are asking. So this is, the first question's asking about cosecant. So you'll wanna, if you didn't take good notes on that, you'll wanna go back to what the slide says about what cosecant is equal to. And if you know your special values of, in this case, sine, then you can find the reciprocal of that to find the special value for cosecant. So we don't need to memorize a whole new list of special values or anything like that. We can use the knowledge that we already have of the unit circle to find these. And same thing for sine inverse. So you'll have to be a little clever. You'll have to look at your unit circle and find where sine is equal to root 3 over 2. And then pick the angle, remember, that's between minus pi over 2 to pi over 2. So of course, as always, if you struggle, I'll be happy to address these in class. I'm sure I will anyway. And I hope you have a good rest of your evening.